We kind of believe that DDN is the best for these large-scale systems because of the properties I'm going to talk about. And I'm also going to talk about a bit of the developments we're putting into Exascaler throughout this year. Who in the audience has heard of Exascaler? I'd like to do a bit of a test. You're usually pretty expert in this audience. So gently breaking into DDN and our products, here we have DDN's AI400X2. We're providing now up to 120 gigabytes a second of read performance, up to 75 gigabytes a second of write performance. That puts it about 20–30% faster than the previous generation, which looked the same, but without a little T for turbo associated with it. And we launched that back at GTC, just not that long ago. It's 15 times, at least 15 times faster than popular, well-marketed NFS-based systems on the market today. It's very efficient. We've been developing this efficiency with NVIDIA for the past 5 years. We installed the first system with NVIDIA, 2017, 2018. And we've been in constant contact, going back and forth on various feature developments since then. We started with GPU direct storage, moving data directly from storage into GPU memory. We were then asked by them to speeden up multi-epoch training of Megatron LM by caching reads inside their DGXs. We delivered that about 3 or 4 years ago. We then noticed that the mmap calls that were being made by many of these AI frameworks weren't running fast enough, and we sped them up, and many, many more. So this has been going backwards and forth for multiple years to get this very efficient system with lots of common features between ourselves and NVIDIA. And reducing cost. I mean, nobody really says DDN's cheap, but actually when you add up the costs of power, space, the network ports we consume, and the amount of throughput we give you per port, per square foot, per watt, we look extremely competitive versus the rest. I'm going to talk about various elements of this. So things are getting tougher. In a good way. I took this little picture out of one of Jensen's talks at GTC 2 or 3 months ago. First thing is, I think Paul mentioned before, we've been talking about checkpointing and data load. So data loads and checkpointing is associated with the AI end-to-end workflow. And everybody kind of gets data loads. Of course, they have to load data in. I've got to train on it. But people forget a little bit about the checkpoints. But Jensen specifically mentioned it. He mentioned it in the context of the next generation systems, which Mark Hamilton was talking about. They're getting extremely large. They're getting so large that they've built, I don't know if Mark mentioned it, but they built a little RAS chip inside the chip to check and try and verify that that chip was going to stay very stable to improve the uptime of these large systems. So this checkpointing is becoming increasingly important. When we developed GPT-3 and Megatron on these systems 2 or 3 years ago, we were running over a few hundred, close to 1,000 A100 GPUs. Our customers now are trying to run across 10,000 GPUs, and so this problem doesn't multiply by 10, it multiplies by about a factor of 100 in terms of uptimes. The second thing he mentioned, and Jensen always says this, and we really believe it as well, and we've said it now for 5 years consistently in this context, in AI context, is that fundamentally it's about cost and energy. Not really capital cost of systems, but overall cost of data center, the energy consumed, and the amount of productive output you get from that. So Jensen's into that, NVIDIA into that, and DDN is very much at our heart as well. I said things are getting worse in a good way. We've been on this trail now, and we've got an exponential graph, like everybody has exponential graphs showing the improvement of GPUs, GPU cycles, flops, memory bandwidth, network bandwidth over the past 5 years. It has been pretty remarkable. NVIDIA's got a more accelerated cycle of release than anything else I've ever seen. So it's pretty much every year we see a new announcement, a new GPU. So it seems like Moore's law kind of accelerated in a kind of different form with this AI systems. But what this means fundamentally is even if you think the storage you have today is probably okay for the next 2, 3, 4 years, it may not be, because these systems are now doubling, quadrupling the need for very fast storage in a very short time frame. So these Blackwell systems are going to be on the market next year, and that's pretty close, and all of a sudden we need 4 times the storage throughput bandwidth IOPS than we needed this year. So it's a never-ending train right now in exponential increases, not only of the models, but of the systems associated with running those large-scale models. And here's my kind of view, and I've extended it recently. This is my kind of view of what happens, what we think about as people who try to build very efficient storage systems. What can we do to make these AI models go faster? And of course, there's analogs in HPC as well. But fortunately for us, it takes quite a nice consistent pattern for all AI frameworks. First, you ingest your data you're going to train on. Second, your data scientists munge that, add metadata, move it around, change it to the correct format, clean it up. And then you go into the distributed training phase. That's when you submit it to your 1,000 GPUs or whatever. And then the first thing that happens is you load your model and load your data into memory or very close to memory on the GPUs. And the data load can take, if your model is not scaling well in particular, up to 60% of the wall clock time, worst case. Then you're going to train, and that's of course the thing you want to be able to do all the time. If you bought $50 million worth of GPUs, what you want to do is have those data scientists training models and producing models constantly. And then we're going to go round in a circle during this distributed training phase. I'm going to move out the yellow lines now. The checkpoint is over there. So typically once every hour, but once every 1 or 2 epochs, we're going to checkpoint the whole model in memory, all the hyperparameters and all the associated parameters. We're going to push them down through the network to secure storage. Right. If you think about, and this goes round and round, this sort of distributed training, round and round in a circle, every hour typically, sometimes half hour, sometimes more. We have a customer in Japan who's trying to keep this checkpointing down to less than 5% of the wall clock time. We've got other customers interested in speeding up the model load. We go round and round this in cycles until every epoch, we're going to check the error of the model. We're going to checkpoint, and then we're going to back propagate to change those hyperparameters, and we're going to go round again. Again, typically on the same data. So we've been optimizing all ends of this model now for, I'd say, 5 years. With the data load, we implemented something called hot nodes. At the behest of NVIDIA, that's going to load the data first from storage, but it's going to hold it in a cache, completely transparent to the end users. End users don't know. And then subsequent epochs, we're going to just reread that, and that's going to relieve the network, relieve the storage from that repeated data movement. The checkpointing, as I say, in this little thing here, can be up to 43% of the time. So that's from a paper done, monitoring lots of different jobs. The time associated with checkpoints can be as much as 43. Typically, it was more like 10, 12, right? But imagine you checkpoint. Sometimes you're going to restart. You're going to have some lost time there because you get to the checkpoint again. There's going to be a rescheduling time. All that time can be as much as 43% of the wall clock time of your cluster. Then you're going to distribute that model. You've got a nice low-error trained model. You're going to distribute it and send it to where it's going to go and run inference. And now we've got this new thing tagged on the end there. We've got RAG. A, when it's being trained, and B, when that model's running an inference. With these RAG models, they're going to be running, could be at the edge, could be in a telco, could be in a data center. Every query it gets, it's going to go off to a large data lake and retrieve some data to augment its answer back to you. So in the context of chatbots, we're going to get rid of this hallucination problem because before answering you, GPT or its equivalent, its successor, is going to check current data associated with your question and verify its answer and give you a bit more truth coming out of that. In terms of storage, that means a new set of low latency storage devices close to where the data is being inferenced. More to come on that. I expect we'll be developing that N square of the next few months. So what have we done? What's the effects and what's the impacts of what we've done? We've improved checkpoints over NFS systems by about a factor of 15. That means that 12% of the time, could be 5% of the time, something like that, we can reduce that to less than 1% of the time. That means 4% of that time is now back for training, and 4% of a $100 million data center is an important 4%. We've also improved this loading, and fast loading of the models, and repeated loading through these multi-epochs. And in the sales way, that gives you back a total of maybe 25%. So some of our customers do run up to this 25% because they've got very intensive checkpoints and lots of data loads using images and videos. Some are less, some are more. But by choosing fast storage, and you're not waiting for I/O all the time, we can release all these GPU cycles, which would otherwise simply be wasted, and the watts will be emitted into the atmosphere and just heat up the air a little bit. So part one is, we believe that through all the optimizations we've done, we give you a significant percentage back on your investment in GPUs. And the important thing is the end users are noticing. This is real. It's all very well me saying this. This is a blog, very nice blog, by a very talented guy called Yi Tae. He's an ex-senior Google researcher. He now runs a company called Reka.ai. What he did, he's in the process of trying to create a whole new startup company around AI. So he's trying to get to the point of training these models and working out the best process to train the models at a very large scale. He's been logging into various clouds that won't be named and using GPU cycles, and he's paying per GPU hour. Probably pretty important how much productive output he gets. And he's been measuring his model flop utilization, how much his application actually gets per GPU hour from real clusters. And he's got quite a long blog with lots of things to say, but the things that I noticed was that he recognizes some of these clouds have poor I/O and poor file systems. And he noticed that checkpoints can result in timeouts or ungodly waits. Lots of GPU hours just going into the ether there, chipping away at cluster utilization. And then the other thing he said was, if we're competing with other users and the other users are just starting to ingest loads of data or whatever it might be, then suddenly your model flop utilization goes down dramatically. Now the point about this is not something we don't know. We kind of believe it at DDN. But we wanted to point out that end users are comparing systems and seeing the impact of storage inside those clusters. So it's not just theoretical, the end users are going to be able to tell. But it's not just performance. What you want to do is take your storage system, reduce its power footprint, reduce its port count, and reduce its space footprint, because typically our customers especially are really constrained on power and data center space. So what we are really doing here, we're a small fraction of the power, right? We're a small fraction of the space. But by relieving 1, 2, 3, even as many as like 10 racks, by reducing and making more concentrated the storage, we're basically creating more space and power for GPUs to run, which is typically what these customers want to do. So it's not stopping. We've recently relaunched this turbo device. This is what I mentioned right at the start. As the GPUs are increasing in power and performance, memory bandwidth, etc., we've got to do the same with our storage. We just went from 90 to 120, a 30% increase. Essentially, you do nothing. You buy a new system, it looks the same, it feels the same. It just goes 30% faster. And that was launched at GTC. We're also adding this year expanded QLC systems. We're already supporting QLC. So QLC is lower cost flash. It's still low latency flash. We treat it extremely well, so you get great performance out of it. But when customers want all flash, and they haven't got the budget for all TLC, then QLC is a great option. We're expanding the options there by allowing you to get not just 2 enclosures as you can today, but up to 5 enclosures. Very large, 4 or 5 petabyte footprint before compression in those QLC enclosures. We can also ship HDD. And typically this is now being, it's slowly migrating towards more of an archive solution, particularly with the large-scale AI systems. So the flash is the thing that's being presented right to the GPUs, but there's space for a tier of much lower cost capacity in the form of HDD. And the cool thing is, by the way, that can all be one file system, all that picture. You can take all of those systems, the HDD, the QLC, the TLC, you can present it as one mount point, and you can use pooling to manage the different pieces. End of the year, you'll be seeing another announcement, the X3. We're going to be doing another boost. We need to keep up with the performance of these things, the memory bandwidth of these things, the network of these things. PCI Gen 5 appliance supporting Bluefield AI400 X3 will be coming out at the end of this year. And what have we been doing in software? Andreas isn't here, but Peter is here, so talk to him for more details. That is skulking in the back. Peter runs our engineering organization for Lustre. I've simplified the roadmap. Essentially, it's in black bits and green bits. If you stare at the green bits, what you'll see they're all about is stability at very large scale, ease of use, ease of management, online upgrades. It's that whole theme of RAS we've been building on because as our customers get bigger and bigger, and as Mark said, they just want to go into production really fast and have it up and stable. We've been focusing down on rolling reboots, faster HA, simple online upgrades, better health, better diagnostics, exporting the monitoring to Prometheus, etc. All of this stuff, the majority of the engineering has been improving health, improving stability for the past 3 years, in fact. But that's not all. QLC, as I mentioned, turbos come out already, larger QLC systems. We're introducing compression to increase the value you get for your dollar spent on your terabytes by adding compression. It's a cool way of compressing data. We do it on the client, which means it's compressed over the network, and it's not throttling your storage system and killing the performance. Very cool feature coming out in the middle of this year. And then you'll see as we move on to Exa 7 early next year, we get to the holy grail of push-button online upgrades. Right now, it's pretty simple, and each stage it gets simpler. Here we go. We've got simple online upgrades. End of the year, or towards the start of next year, push-button online upgrades as we move on to Exascaler 7, and we jump a new Lustre release. So, conclusion. We've been working very hard with NVIDIA. Things are really rolling right now. As Paul said, well, he mentioned that in this quarter, we've already sold more than we sold the previous year. Actually, the same has been true for the past 3 years. You look at the 2 years ago, it was the same. Last year, it was the same. And this year, it's the same again. So it really is an exponential growth in this AI area. We still love HPC, and it's a big part of our business. But we have been focusing on AI to try and get over the hump of these very rapidly expanding AI models as they go to multiple tens of terabytes in model size and handling those data loads and checkpoints. We've done that with a huge amount of work between us and NVIDIA, and that's resulted in these X2s. And we'd love to talk to you more about it in more detail, talk about roadmaps in more detail. I'm sure Peter Jones would love to talk to you about the detail of the Exascaler roadmap as well. And now I'm going to let Sven talk to you about something completely different.